Um, we have an image. This is actually a novelty toy. It's known as a drinking bird. I actually have one in the classroom. I'll get it out and you guys can play with it later. But it's an example of Carnot's engine. It contains methylene chloride mixed with dye in its abdomen. That's that little red stuff right there, and which boils at a very low temperature, about 100 degrees Fahrenheit. Um, to operate, one gets the bird's head wet. As the water evaporates, the fluid moves up into the head, causing the bird to become top heavy, and it'll dip down in the water. Then, as it cools, um, this cools down the methylene chloride in the head, and then it'll fall back down to the abdomen. So as um, and essentially the bird will go up and down, up and down. And it really only requires a small, just a very tiny amount of input energy, usually the original head wetting, and the bird becomes a perpetual motion machine of sorts. Over time, it'll stop, but it will go for quite some time, and this is all due to heat energy. So we know from the second law of thermodynamics that a heat engine cannot be 100% efficient, since there must always be some heat transfer of QC, the colder temperature. So, which is often like waste heat. So let's jot that down real quick. So, shoot, boy, we start off with the errors, huh? we start off with all these problems. It's a little frustrating. All right. So, oh, that's very frustrating, actually, now that I think about it. All right, so heat transfers not 100% efficient. And QC is this almost always just gets released into the environment, right? When we think about how most heat engines work. And so just to kind of recap, remember for a heat engine, we have our system, perfectly drawn system. Here, let's do it this way. So we have our system here. And so then we have heat coming into it, QH. We have a little work coming out, and then we have some heat leaving. Okay. And the work is the difference of the two, so remember that work is equal to, this is very frustrating, work is equal to QH minus QC, or work is equal to Q net, right? Because this whole thing equals Q net. All right, so the total net heat. All right, so then the question was answered theoretically in 1824 by a French, and I said Carnot, but it's actually pronounced Carnot. And he did some studies during the Industrial Revolution, and he devised a theoretical cycle now known as the Carnot cycle. And the Carnot cycle is basically the most efficient cyclical process possible, using the second law of thermodynamics, that can be restated in terms of the Carnot cycle. So what Carnot actually discovered was this fundamental law. Any heat engine employing the Carnot cycle is referred to as a Carnot engine. So what is crucial about the Carnot cycle is it defines it as that only reversible processes are used. Irreversible processes involve dissipation factors such as friction and turbulence. This increases the heat transfer out to the environment, QC, and reduces the efficiency. So I'm trying to think of a good way to say it, but I'm gonna show you an image here. So this So I gotta remind you guys of a couple of things. Well, let me just say this. So, stated in terms of reversible processes, the second law of thermodynamics has a third form. Our Carnot engine has operating between two given temperatures, has the greatest possible efficiency of any heat engine operating between these two processes. Furthermore, the engines employing only reversible processes have the same maximum efficiency based on the temperatures, of course. So I'm going to put a figure up, and so this is what we talked about last time, just a simple heat machine. And so let me show you guys. So this is what the PV chart for a Carnot cycle is, and it's very similar, but it's slightly different. So I gotta clean this up a little bit. I got some stuff in the way here. Somehow oops, I want this. There we go. So very similar to what we talked about yesterday. But Carnot is determined as a perfect heat engine. Well, let me show you some of the math behind this, okay? So remember from yesterday, and I'm not going to redo the derivation, but we said that the efficiency, after we did some fancy math, was just 1 minus QC over QH, right? And so you're always going to lose a little bit here, so your efficiency will always be less than 100%. Remember, 1 is 100%. So no heat transfer is 100% efficient. That's just the way it works. However, what Carnot found was that for the perfect heat engine, the ratio of QC equals the absolute temperatures of the heat reservoirs. He discovered that QC over QH, whatever that ratio is equal to the temperature differences of the heat reservoir, because this is a reservoir. And this is a reservoir. So if you think about that, and and remember that this is a ratio that will be reduced down to a decimal, So Carnot's approach was why don't we just think of efficiency? Oh, that is very frustrating. There we go. We don't necessarily need to measure, and it's a lot easier for us to measure the temperature of the reservoirs than it is to actually measure the actual heat entering the system and leaving the system. I should probably note that all this stuff has to be done in Kelvin, right? Our temperatures should be measured in Kelvin. So then what's the goal? Well, you want to make this ratio as close to 0 as possible, because that gives you the most efficient. So what you want is you want TC over TH to be as close to 0 as possible. You want that to approach 0 if you can. Okay? Well, how do you do that? Well, the easiest way to do it is to let the cold reservoir approach 0, mathematically speaking. So if I can get TC to get pretty darn close to 0 Kelvin, then it doesn't matter what the heat is on the outside, right? My ratio will be pretty close to 0. And that was just a mathematical kind of blip in it. The problem is this is in Kelvin, so when what we're talking about is absolute 0, which, by the way, we can't do. We can't do. We get pretty close though, and it requires a lot of energy to do that. So the energy that we would be using to approach absolute 0 doesn't necessarily outweigh, in other words, the efficiency we gain in heat efficiency, or the transfer of the efficiency of heat transfer, doesn't make up for the fact of all the energy that we would use to achieve a near absolute 0 for our cold reservoir. But it's fun to try, right? So if we take that information and we go back and we look at what happens in this scenario, heat comes in, right? So we start here, high pressure, low volume. Heat comes in, that will increase the pressure, or not the pressure, the volume, increases the pressure. I keep saying it wrong. Increases the volume, but the pressure lowers. And then you have this adiabatic expansion, right? So you increase the volume a little more. Then you have this isotherm where the heat leaves. As the heat leaves, our volume goes down, but our pressure goes back up. I'm sorry, I'm pretty sure. You guys know that up and down is pressure, left and right is volume. Okay, I'm sorry, I keep saying the wrong thing. So at this point, the pressure will increase because there's heat coming into it, and the volume will decrease a little bit. So that's basically Carnot's engine. So employing only reversible isothermal adiabatic processes, the heat engine QH, or the heat transfer from QH, occurs into a working substance during an isothermal path AB, which takes place at a constant temperature TH. The heat transfer QC occurs out of the working substance during an isothermal path CD, which takes place at a constant temperature TC. The net work output, W, equals the area inside A, B, C, D, A, Also shown in this chart of a Carnot engine operating between hot and cold reservoirs and temperatures TH and TC. So any heat engine using reversible processes operate these two temperatures with the same maximum efficiency as the Carnot engine. So let's see how this applies to something like a nuclear engine or a nuclear reactor. So a nuclear power reactor has pressurized water at 300 degrees Celsius. Higher temperatures are theoretically possible, but practically, from a practical perspective, not good, right? That's a lot of pressure. Due to limitations of materials used in the reactor. The heat transfer from this water is a complex process, which I'll show you in a second. Steam produced by this process in a steam generator is used to drive a turbine, and the turbines are connected to generators. Eventually, the steam is condensed to water at 27 degrees Celsius and then heated again to start to cycle over. The maximum theoretical efficiency of the heat engine operating between these two temperatures, right? So, all right, so first things first, let me show you what we're talking about. So this is a typical nuclear reactor. All right, so you have your control rods, and this is where the nuclear reaction actually takes place. So in the core, that gets really hot, okay? Really, really hot. And so what that does is that will heat up this water, and then this water will actually get so hot that it becomes steam. The steam line comes down here, and once it enters here, it's going to push these turbines. Those turbines are going to turn a generator, and then the water will go up to a cooling tower, and basically air just cools it off, and then it comes back down cold. The cold water is on the bottom, gets siphoned back into the system, and this just goes around and around and around. And actually, we were asked, I kind of got excited of myself. It says we were asked to calculate the maximum theoretical efficiency for a heat engine operating between these two temperatures. So how do we do that? Well, it's actually quite easy, right? So we said using Carnot's approach or cycle, we just need to know the temperatures of the reservoir. So we have the cold temperature versus the hot temperature reservoir. So in this particular case, our efficiency is equal to, and we got to do this, remember this has to be in Kelvin, degrees Kelvin. So 300 degrees Celsius, or did they give it to us in Kelvin? No, they said 300 degrees. So if 27, remember we gotta add whatever our degrees are in Celsius, we gotta add 273 to get Kelvin. So if we do the math on that, 27 plus 273 is 300. And then we had 300 degrees Celsius plus 273 is 573. And so if you do the math on that, the efficiency, if you plug that in a calculator, is about 47.6%. Okay, so that was pretty easy. That's how you calculate the efficiency. And it's not that hard. We just need to know the temperature of the hot reservoir and the temperature of the cold reservoir. And those aren't the actual terms, but you've got one temperature that's warmer, one that's cooler. Hot and cold works just fine. So a typical power plant's actual efficiency is about 35%, a little better than 0.7 times the maximum possible. So remember, this is maximum possible, right? We're going to lose a little bit of energy because we have friction turning these turbines, right? Like it can't possibly be, 47.6. There's some of the energy gets used up doing other stuff. Electrical, which is 35% still isn't bad. Electrical power stations that fire coal and natural gas actually have about 42%. So they're not that bad. The nice thing about this is that it's a very small amount of nuclear material that actually will generate large amounts of heat, which is what we need to generate the electricity. The cold reservoir temperature of these stations, and so this is the same process. So if I had coal, the only thing that would be different in this image is if I had coal, you'd have like a fire here where the coal is burning, right? So if I had coal or natural gas, I basically would have like some sort of fire. Here, we'll draw a fire real quick. So you'd have like some sort of fire underneath it. That doesn't look like fire at all. So you'd have like... Oh, don't worry, I got the fire going. But it looks just like fire, doesn't it? So basically the fire will boil the water and the whole thing will basically be the same. The cooling tower might be slightly different, but that's basically how it works. And so here's an example of what the cooling towers are. If you're always wondering what those towers were, now it might make a little more sense. And there's an evaporation process, which is why we lose a little bit of the efficiency. And so let's look at one more image. So what I have here is these are what real heat engines look like that are less efficient than Carnot engines. Figure A is a real engine is a real engine that uses an irreversible process, reducing the heat transfer to work. Solid lines represent the actual process. The dashed lines are what a Carnot engine would do between the same two reservoirs. So it's just slightly different. And then for part B, we have friction and some other dissipation processes in the input mechanisms for the heat engine conversions. Some of the work output into the heat transfer into the environment. So, this is work done against friction goes into the cold reservoir, right? So if we scroll back up here, the second image is pretty accurate, describing what happens, right? So if we go to this process here, well, there's friction here, isn't it? Well, some of that friction will dissipate as heat. The heat might get absorbed by this water, but eventually that heat, because we're past this process, it'll go to the cooling tower and then it'll cool on the bottom. And so that's what they're saying, is it leaves the system, sort of. And there's also work that overcomes friction itself. So this part of that energy gets used up. You could think of it as like, it's just work overcoming friction, and friction creates heat. And where does that heat go? Well, it's going to go to the cold reservoir, right? And that's basically it. the whole point of the homework really is just this part right here. So this is the main point of the homework, is that you don't need to calculate the individual temperatures in a Carnot engine. Well, it's 2 points. A Carnot engine, we can use the cold reservoir temperature over the hot reservoir temperature, and then also to get the most efficiency, you want that cold reservoir as close to 0 Kelvin or absolute zero, but we can't do that. This is a theoretical thing, but you can, for example, here in the Midwest in the wintertime, that cold reservoir for a nuclear, we have several nuclear power plants in the area. That cold reservoir gets really cold in the wintertime. So anyways, that's it.